Okay, let's go through the contents of this video first. First, I will explain the MATLAB's digit data set, and then I will discuss some pre-preparation of the data set. After that, I will explain the structure of the convolution neural network. That means some theoretical part. And then I will explain the various layers of CNN and different training parameters. And after that, I will explain the MATLAB code of training and validation, followed by the MATLAB code of discrete testing. So let us go ahead. But going ahead, I recommend you to watch following these two videos. The first one is the introduction to the deep learning, where you will get the more theoretical input about the deep learning, and that will help you to understand this current video. The link is given in the description. And the second video is about the MNIST data set, where you can get the idea that how you can convert that data set, which is in a complex IDX or CSV format, to simple PNG and JPEG images. So that is also very important to understand this current video. The link is given in the description. So first we will see the MATLAB's digit data set. Actually, the MATLAB itself includes a digit database, so we don't need to download the data set from some other external source. This digit data set actually consists of 10,000 grayscale images of handwritten digits, and each digit has the 1,000 images in the respective folders. As you can see, we have the 10 folders, and each folder carries 1,000 images of each digit. So these images are of size 28 by 28 pixels, and they have the associated label also. So these are a few examples of these digit images you can see. And this digit data set you can find from the following MATLAB directory. So you can see you go to the installation folder of the MATLAB. From there you go to the toolbox, and then NNet and NN demos, and then NN datasets. There you can find this digit dataset. So let me explore this for you. So let me go to the Explorer. So when you go to the Explorer, you go to the installation folder. That means go to the C directory, program files. There you can locate the MATLAB, and inside MATLAB are 2018, that means the version folder, and then go to the toolbox. So this is the toolbox. There you go to the neural net, NNet. So this is your NNet folder, and inside NNet you will get NN demos, and then NN dataset. So this is the folder where all images are stored. So let me open it. So here you can see the digit dataset folder. So these are the 10 folders. You can see named 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So let me open the 0, and here you can see all the images of 0. Similarly, if you open 1, you get all the images of 1. So each folder actually carries 1,000 images. So you can directly access this place of these images by writing codes, or you can copy this folder, I mean this digit dataset folder, to your another local directory. So let me jump to the presentation. So now let's do some basic preparation for this data set. So what we will do, first we go to this directory as I have shown, and we will copy these folders to some other working directory where I will write my program, MATLAB program. So that MATLAB program will also reside in the same directory. So I can show you that what I have done. So let me open. So this is my the different working directory. I mean this PC in the drive E, exploring technologies, video 22. So this is the different working directory. So where I have copied this dataset folder, you can see it's lying here, and these 10 folders are inside this. And here I will write my MATLAB program. As you can see, these are my MATLAB programs. So for the training, I will take 750 images from each folder. So since there are 10 folders, so there will be the 7,500 images for training, and the remaining 250 images I will take for the validation. So there will be the total 2,500 images that will be used for validation. And this distribution of images we will done by writing MATLAB codes, not manually. Okay, so when you go to the program, you will see that this distribution in 7,500 and 2,500 will be done by writing MATLAB codes. Now let's see the structure of the convolutional neural network. The convolutional neural network is one of the most popular type of deep neural network, which is known as a CNN or ConNet in short. A CNN involves the learned features with the input data and uses the two-dimensional convolution layers, so making this architecture well suited to process 2D data such as images. So this is the general architecture. Here you can see you have an input image which goes to the different series of operations such as convolution, and then rectified linear units, that means ReLU, that is a activation function, and then max pooling operation, and so on. So this we get the repetitive operations, the same operations we get for different layers. And in the last we get one fully connected layer which is used for classification with a softmax function. So here in this figure you can see that in the convolution we have the different convolution filters. You can see this is small squares. Each square is a convolution filter. So these filters are used for convolution with the input image, and we get some output. So this output is fed to the next level. So same operation is done. So at each stage we have the convolution filters. So they keeps on updating with the different types of images during training. So that's why they get features from the input images. This is another look of your CNN. Here you can see that the input image goes to the convolution, and then ReLU operation, and then max pooling. So this operation is repetitive, and it goes through the various such similar layers. And in the last, that is known as the classification, we have fully connected layer and then softmax layer, and after that you get the output in different categories. So if you see the different layers, you can group like that. First we have the input layer that we have to define when we will define the deep neural network, I mean CNN in the MATLAB. And then we will define various layers during the feature detection, which are 2D convolution layer, as I have explained. And there is one more batch normalization layer that is not shown here in this figure, but it will be used, and then ReLU layer, and then max pooling layer. Okay, and in the last we have a fully connected layer, softmax layer, and then classification layer. So these are total number of layers which will be used to implement any CNN in the MATLAB environment. Of course, this middle one will we use repetitively. I mean, these are not only the 4, we have different bunches of these 4 layers in between input and output. Now let's see the MATLAB syntax of these layers and their specifications. So first let's see the input layer. The input layer of this CNN is defined by this syntax. So input layer, this is the command, and in bracket you define the MNN, and you give some name to this layer. It is optional, you can omit it. But what is this MNN? Actually it depends on the input image. So if your image is of size m by n, and it is, let's say, the grayscale, grayscale, then your specification will be like this: m comma n and then 1. 1 because of the grayscale, it has only the single layer. And if you are using a color image of size m by n, then you will specify this as m by n by 3, because there will be the 3 layers of RGB, right? So here in this example, you can see that 28, 1 is given. It means I'm using a grayscale image of size 28 by 28. So this is the grayscale because I'm taking only the one channel. So in the input image for my present CNN, which I will implement, will be a 28 by 28 image of grayscale. And the second is, as I said, is the convolution layer. This is the important layer which is responsible for the feature extraction. These filters keep on updating with the training data, and this is the general syntax by which we will implement in MATLAB. So this is a command: convolution 2D layer, filter size, then number of filters, stride, which is which has the value n, and then padding, which has type same, and you give some name to this layer, let's say conv1. This is optional, you can omit it. So this is a general example. So here 3 means that is your filter size. I mean those small squares as I have shown in the previous slide. So the filter size will be 3 by 3. So we'll have the filters of size 3 by 3, and 8 means that is the number of filters. So number of filters actually means this is the number of neurons in this layer, and the stride and means the default value of stride is 1, but you can give 2 and 3 also. The stride means actually by what pixel value the filter will shift to the next group of filter. You know that how the filtering is done. So suppose this is the image pixels, and we have a 3 by 3 filter, so we get the first 3 by 3 group of pixels, and we do the convolution. After that, this filter moves to next group of pixels, 3 by 3 pixels. So this shift of this filter, you can do either 1 pixel, 2 pixel, or 3 pixels. So that is known as a stride. So the default value is 1, as in this case, since we have omitted this, it means the filter will shift by the 1 pixel. So if you go to the stride 2, your size will be reduced in the output. And then padding. Padding is also required to cover the first column or the first group of pixels. So, and after that, padding same means after doing padding or convolution, the output image or output, whatever we will get, that will be of the same size as of input. Okay. And next is the batch normalization layer. So it normalizes the activations and gradients, making network training an easier optimization problem. And it also speeds up network training and reduces the sensitivity to the network initialization. So it is used just after the convolution layer, and you can say that it is used in between convolution layer and the ReLU layer. And the syntax is simple. You just write the name batch normalization layer. This is your command, and in the bracket you can give the name to this layer. You can omit it also. There are no other options. And after that, we have the ReLU layer. That is the most common nonlinear activation function, that is known as a rectified linear unit. So this is this function is like this. This function is like this. So for all negative values, we get the 0 values, and for all positive value, we get the same value. There is no change. So you can see that if you have the values after convolution, let's say -1, 0, 2, 4. Then after ReLU, what you will get? You will get 0 because of the -1. 2 will remain 2, 0 will remain 0, and 4 will remain 4. So that is the ReLU operation. So this is the MATLAB syntax. You can give the name, no other options to define. And then max pooling layer after that, it is again a very important layer. It is used for the downsampling operation. So that reduces the spatial size of the feature map and removes the redundant spatial information. So after ReLU, we go for the max pooling, and max pooling operation is easy. First see the syntax. We define the pool size and then stride, and then we give some name. So stride I have already shown. That means by what pixel you shift the window of size, pool size. So here in this example you can see that I am using the max pooling of the 2x2 window. So it means after the convolution or after the ReLU, I will use a 2x2 window. So inside this 2x2 window, if I get let's say following values in this window, then after the max pooling I will get a single window or single value. So these 4 values will reduce to a single value, that will be the 16. So max pooling means I will take the maximum out of these 4, so that is 16. So the single value will be the 16. So that's why how I'm doing the downsampling, to reduce the size and complexity or reducing the redundancy in the network. And after that I have the fully connected layer. It is important. So fully connected means the all neurons of this layers are connected to the all neurons of the previous layers. So this fully connected layer combines the features to classify the images. So this is its general syntax in the blue. So it asks the output size of this layer. That means you have to define the number of neurons in this layer. So in this case I have taken the value 10. So it means there will be the 10 neurons in this fully connected layer. Why 10? Because this output size actually depends the number of categories in the output. Okay, number of classification, or you can say number of categories. So in this case in the digit classifications, I have total 10 cases from 0, 1, 2 to 9. So these are total 10 outputs. So that's why I'm taking the 10 number 10 here as the output size. And suppose you are using the CNN to recognize, let's say, only the 5 different types of objects. Okay, 5 different types of objects. So you will define 5 here. So that will depend on the how many different objects you are recognizing using the CNN. And the next layer is the softmax layer. So the softmax actually it's an activation function which normalizes the output of the fully connected layer. So the output of this softmax layer consists of some positive numbers that sum up to the 1. So it means it takes numbers from all those 10 neurons and sum them to a single one. So that will give the final output corresponding to a particular category. So which can then be used as a classification probability by the classification layer. So this is the general syntax, softmax layer. You can define the name of this layer. Actually, these names are used to plot or to see the structure of the CNN once it is declared in the MATLAB. Otherwise, there is no use of this name. And the last layer is the classification layer. That's the final layer. So this layer uses the probabilities written by the softmax activation function for each input to assign the input to the one of the mutually exclusive class and compute the loss. So that's the final output. So each category gets some number as the output, so which are known as the probability classification probabilities. So this is the general syntax, classification layer, and name. That means you can give some name to this layer. For example, I have given the name output classification. And now let's see the different training parameters. Those will be used in the training of the CNN. So in the MATLAB, we give the syntax, and this is the expansion of this option. So in the training options, we define the solver name, such as we have defined as GTM here, and different various other parameters such as learning rate schedule, which is piecewise, learning rate drop factor 0.2, learning rate drop pre-rate, maximum epochs for training, batch size, and then if you want to plot the progress, then plot is also given. That means when you train your network, you will get the progress of the training with the epochs. Okay, with a number of epochs you can get the training. That means your output versus epochs. And actually there are various other parameters, and if you want to learn all those parameters, you can go to the MATLAB documentation. I'm not explaining all those, that will require too much time. Actually the important thing is solver. I mean, as I have written SGDM, I have actually the three different options. The SGDM actually represents the stochastic gradient descent with the momentum. So if you specify it, you need to specify the momentum rate also along with it. And then next is the RMS prop optimizer, and it needs actually the decay rate of the squared gradient moving average. And if you use ADAM optimizer, then it also needs the decay rates and of the gradient squared gradient moving average. And next important thing in the training option is the use of the hardware. Actually, you can harness the power of the hardware which you are using, as your laptop or as your very powerful workstations or other. So you can define that option also, for example, with this command execution environment. For example, right now I will in this video train my CNN with a CPU, because my laptop has no dedicated GPU. It has only the integrated GPU. So the main power will be used as a CPU. So but if your computer has a GPU, dedicated GPU such as NVIDIA, etc., you can use that power to train. And you can also use a multi GPU. If you have the multiple GPU cards in a system, you can use that power. Or if you have the parallel computing environment, then you can use that power to train your big networks on millions of images. So this is the MATLAB code for training and validation. So let us understand line by line. First, we have to define the path of our data set. So as I said, I have stored that dataset folder which has the name digit dataset, which I have shown in my directory, in the current directory, which has the E exploring technologies video 22 digit dataset. So in this folder, I have all those 10 folders which are consisting of 10,000 images. I mean 1,000 images of each digit. So first you have to give this path of dataset folder. And next is reading digit images from image database folders. That means you have to read those images using this command, MATLAB command. So all images will come to the digit images array MATLAB variable. So image data store. So this is your path which you have already given here, and include subfolder true. It means it will look into the various subfolders. Obviously in digit dataset folder there are 10 subfolders. If you make it true, then it will go inside those subfolders. Label source, and then it will take the folder names also. So all are required, and all information will go to the digit images variable. Now as we said that we will distribute the images for training and testing. So we will keep 75% images for training, and remaining 25% for testing. So what I am doing here, I'm taking a variable num train files means 750. So since each folder includes 1000 images, so out of those 1000, I'm taking the 750 images as training images. There is another way of defining it. You can take the value num train file equal to 0.75 also. You can take any value between 0 and 1. So that is another way of declaration of this variable. So this is the absolute declaration. That means you are exactly defining the number of images for the training 750. And here you are just defining 0.75 means in terms of percentage. MATLAB accepts both. So this percentage actually is useful in the case when you have the millions of images. So instead of writing a million number here, you can just give a percentage of division. That means 0.75 or something else. So now this is a MATLAB function split each label. So that means it will split the total number of files in 750 and 250. So that will go to your train images folder and then test images folder. So when you execute this, so all images which are stored in digit images, and you are defining the num train files, that means 750 you have defined, and so all 750 images from each folder will go to the train images. So since there are 10 folders, so there will be 7500 images will go to this train images, and remaining will go to the test images. So remaining are actually the 2500. So 2.5k images will go here, and 7.5k images will go in this variable train images. And here I am using an option that is randomize. So randomize means it will take random 750 images. Okay, instead of taking sequentially from the first, it will take random images. Now this is the syntax of actually the building CNN. So see carefully. So first we have to define the different layers of our CNN. As I have already explained the different these different layers and their syntax, so it is now easy to understand. First we have to define the input layer. So you have defined, so it will accept the image in the format 28 by 28 by 1. It means it will accept the grayscale image of size 28 by 28. And then next is the bunch of this layer which includes the first convolution layer. 3 means it will have a 3 by 3 filters, and number of neurons, that means number of filters are 8. Padding is same, and the name of this layer is conv1. And then after that we have a batch normalization layer, and then after that we have the ReLU layer, and then max spool layer. Here in the convolution 2D layer I have not given the stride, so the default value of the stride is 1, but here in the max spooling layer the stride is 2. So obviously it will reduce the size of the output, and the size of the max spooling is 2 by 2. So at once it will take 4 values and it will convert them into a single value, as I have explained in the previous slide. After that the same layers are repeated. Okay, so this bunch of layer is repeated, but you have to increase the size of filters. That means the number of neurons. So that will give more complexity to your network and more strength or capability to your network. So in the first convolution the number of layers are 8. Number of neurons or filters are 8. In the next convolution the number of filters are 16, and the rest of the things will remain same. And then we define again the similar bunch of the layers, and here I have increased the complexity. So here you can see that number of neurons or filters are 32, and again I have the same bunch of layers. Here I have increased the complexity to the 64. So this is how the complexity is increasing layer wise layer. And I think these number of layers are sufficient to recognize these images. So I ends up here, and one important thing is that in the last bunch, this is the last bunch of layer, Here the max pooling layer is not used. As you can see, it is missing. And the last three layers are important, as you have seen. The one is a fully connected layer, and here I have given the number 10, which is actually equal to the number of recognition or number of digits or number of objects in general case, and then softmax layer, and then final classification layer. So this is the general structure of my network. If you want to see graphically this network, you have to execute these two commands. So you first convert all these layers to a group using the layer graph command, and then by plotting function you can actually plot what layers I have in my networks, how many layers I have in my networks. So when I will execute this command, you will be able to see the structure of the network. And these are now the training options. You can see we have defined the SGDM solver, and then we have defined the initial learning rate, that is 0.01, maximum epochs 4, and then we shuffle the data at every epochs. Validation data, in the validation data you have to give the name of that MATLAB variable, which includes all those 2500 test images. And then validation frequency 30, what was false. And yes, this plot training progress, actually when you execute it, you will have a graph showing the training of the learning. And then this command nat equal to the train network, so it will initiate the training. And once the training is finished, you get all the weights and everything in this single variable nat. So this nat is a variable, it's a CNN which is trained with your data, and you can actually export this to somebody else. So in train network you have to define the training images, and then these layers which you have already defined, and then training options. Okay. So once training is done, now I can do the classification. So this is the function which is used for classifications. So you have to just pass this network structure net, and then you can use your images. For example, in the test images, I have all those 2.5K images. So the classify function will classify those images along with their labels. So what I am doing here, I am getting the labels of classifications, and then I am finding the accuracy, that how many images are correctly recognized. Okay, so this will give me the accuracy in the percentage. So let me run this program in MATLAB, and let's see how the training is done. So let me go to the MATLAB. So this is my editor, and this program is already written. So I will simply press this run button. So let me press run. So execution will start after changing this folder. So let me go to the workspace. Yes. So this program is running now. You can see that MATLAB is busy right now. So I have to wait till it finishes. So it will take some time, because 10,000 images, sorry, 7,500 images are in training, and 2,500 images are in testing. So it has to process 10,000 images. So yes, in this plot you can see the structure of your network, and this is the plot of the training. You can see that how the training is approaching to the final value. So, and this is actually the loss or error, which is going down as the epochs are increasing. So you can see here that this solid blue is a training which is smoothed, I mean the filtered one, and actual training is just a light blue which has lots of variation, and then this dashed line is actually the validation or testing. So here you can see that it is reaching towards 100, and this is reaching towards 0. So it's going good, and here you can see the progress of your training. So epochs are 3 now out of 4, and iteration per epoch 58, maximum iterations are 232, and here you can see all the detail, and here you can see the hardware detail also. The hardware resource is a single CPU in my laptop. Okay, that's the initial learning rate, and learning rate is a constant. So let me wait till it finishes. So you can see that all epochs, this is epoch 1, epoch 2, epoch 3, and then currently epoch 4 is in progress. So the learning, you can see very well it is going. You can see the output has almost reached to the 100. That means the error has reached to almost 0. So very fine result I'm getting right now. So okay, so the final is obtained. It means the training has finished. So let me minimize it. So here you can see that accuracy I achieved is a 99.8%. That's a very well fine one, and this accuracy actually achieved by validating those 2500 images in the test folder. So now let me test some of my own files. So I will go to the discrete testing. So that function I have already written, that is a function for testing. So first let me go to my presentation. So this is actually code for discrete testing. So here I will choose any of my file, any of my image as the input, and I can see that whether it is recognized correctly or not. So here I am reading any of my file. So executing UI get file, you will get a Windows dialog box where you can choose your file. So by reading I am read, I can read the file, and that will go to variable I, and you can show that image what I have read using I am show, and this image is passed to the classify function, as I said. So your NAT, which is already trained, so NAT is there, your CNN is there, and the input image is there, so it can classify. So you will get a corresponding label, and that label is printed as the title on that image. So you can have an idea that I have recognized the image correctly or not. So let me jump to the MATLAB and run this program. So this is my editor, and this program is I have already written, so I am just running it. So when I run it, it asks me to choose my file. So I go to the digit data set, and then I can choose any of the image. So I choose this, and let's see what happens. So I get this output. So you can see that digit recognize is 0. So it is correctly recognized. So let me try one more. Actually, I am taking the image from the same folder which is used in training and testing. So I'm not really sure that whether this image is taken in the training or not. So if it is taken in training, then there is no need of actually testing it. Obviously the output will come definitely correct. So digit recognize is 8. So the good thing is that I can give my own image. So I can create it. So first go to the paint, MS Paint, and I will create a 28 by 28 size image. So let me create a 28 by 28 image. Okay, this is 28 by 28. Let me enlarge more and fill it with the black, and then with the white I will write the digit. So let me write something on this image. So let me write, let's say this is 2. So this is my own image, and I will store it. So file, save as, and then BMP, and since I want a grayscale image, so instead of 24-bit you use just 256 color. So your test image will be grayscale. So let's this name is T1, save it. So let me go to the current directory and find where is the T1. Okay, this is the T1. You can see this is the file T1, and I will give this file as input to this testing program. So I will select this T1, this is T1, and let me open it. Okay, so this is the output. You can see that digit recognized is 2. So my program is working well and it is recognizing correctly the digits. Similarly, you can give all other different types of images. So that's it for this video. I hope you have enjoyed this video, and I hope that you have learned that how to create your own CNN and how to define the different layers and how you can train it and test it. So I really thank you all for watching this video. Goodbye.